Hi everyone. Today we will talk about the timing of the FID signal received by NMR, and we will focus on two parts. One is the dead time of the MRI instrument, which is related to the instrument hardware and it determines the initial position of the instrument to acquire the effective signal. The other is combination of our corresponding pulse sequence to obtain the signal at the corresponding time. For example, setting the echo time of the corresponding sequence. This part is mainly related to the purpose of our experiment. When we test with NMR equipment, the instrument needs a certain reaction time to receive the signal, which is generally called dead time. The graph below is the hard pulse FID sequence. We talked about that before. Well, from this figure, it appears that the signal is generated immediately after the 90 degrees pulse ends. In fact, the graph ignores the response time of the instrument. Well, let's add this part and then look at the following graph. The 90-degree pulse is applied at the time t1 and ends at the time t2. This time includes the coil ringing and the reception waiting time. At the end of the RF pulse, the RF energy in the RF coil does not disappear at once, but is a short escalation decay process, which we call ringing. During this time, the NMR signal cannot be effectively acquired, which is called the RF coil dead time, the size of which is determined by the RF coil. MRI uses a filter to filter the signal, which requires an additional period to allow the filter to reach a stable operating state. This waiting time is called the receiver dead time, and its length is determined by the hardware condition of the receiver. The dead time is in the microsecond range and varies from the instrument to instrument from a few microseconds to tens of microseconds. That is, the instrument acquires useful data only from the moment t3. The instrument dead time is an important indicator, but it is of different importance for different applications. For example, for some sample with long relaxation, the relaxation time is of the liquid sample is generally long, such as pure water, which has a very slow relaxation and a few tens of microseconds of signal, where loss has a little effect. But for some fast relaxation samples, such as the solid samples, like plastics, polymers, such samples, its relaxation is very fast, maybe a few microseconds or even or less. Then this time, the instrument dead time is very critical. The instrument dead time is too long, which will lose the fast relaxation part of the signal. We need to shorten the instrument dead time as much as possible to acquire more original signals. Let's look at the effect of instrument dead time on the acquisition of a short relaxation sample signals. Due to the dead time of the instrument, the initial signal acquisition starts from T3. For sample A, this part of the signal between the T2 and T3 is lost For sample B, due to the faster relaxation, most of the signal is lost when the sampling at T3 time. And the signal to noise ratio is reduced. Also, the analysis of the sample by the signal is discounted due to the loss of the signal. For the sample C, the relaxation is even faster. T3 before the signal has decayed to zero. At this point, although the NMR phenomenon occurs, but because the relaxation is too fast, the decay is completed within the dead time of the instrument. The instrument cannot collect the NMR signal, and the signal is all lost. So this type of sample cannot be tested. Here we have looked at the comparison of the three samples. For the signal with shorter relaxation, the dead time is very critical. If the dead time is longer, we may lose the important information and even cannot test the sample. Well, this experiment, I will upload the video later. So for the timing of the sequence, we talked about it is all here. Thank you.